Welcome family, friends, and faculty. Today I will present to you my doctoral research project titled Capturing Tacit Knowledge Through Augmented Reality. The purpose of this thesis is to expand on the topic of tacit knowledge with a focus on augmented reality as an integrative component towards the engagement of users and clients in the design decision-making process for future applications. 3 augmented reality scenarios are explored to demonstrate the methodology of smart device augmented reality application to illustrate the potential process for design communication. To showcase this potential, 3 selected scenarios include a simulation dealing with a visualization of architecture element, an assembly assisted by holographic information, and a fenestration design with daylighting metrics. A project's success is dependent on the wishes, needs, and satisfaction of the client, which is to be highly considered and managed by the architect. Successful projects are born out of relationships between designer and client. Successful relationships are the fundamental component which are born from the cultivation of client education and understanding of architecture knowledge, and one of many factors towards successful relationships. The cultivation of a client's education is the alignment of the architectural understanding between designer and the client, while clients may undergo a process of habitus shock, which is described as a field of unfamiliarity, in the case the architectural habitus. The architectural habitus comprises of a unique set of skills and knowledge socially acquired through experience and practice, continually reproduced over generations. It is the duty of an architect to guide the client's understanding during the project, cultivating the client's architecture know-how and realigning project goals. The nature of the habitus that it entails can be described as a knowledge that is known as tacit knowledge, which is specified knowledge that is not easily articulated nor communicated as described by Michael Polanyi in 1958. Tacit knowledge has its parallels. Explicit knowledge was described as knowledge that can be documented, stored, or easily reproduced. General examples of both types of knowledge can be seen in the following: explicit knowledge as guidelines, articles, or manuals, as well as tacit knowledge as aesthetic sense, decision-making, or strategy. To put in perspective, the 2 types of knowledge can be seen in bike riding. One can follow a set of explicit instructions, knowing the fundamentals, and may not yet be able to grasp the feeling of it, but on the other hand, one may be assisted through tips and words of wisdom from another, sharing their past experiences. And through trial and error, the rider will slowly get the hang of it. Edward Rogers, Chief Knowledge Management at Goddard for NASA, explains that transfer of tacit knowledge from one person to another can be seen in context sharing and mentoring. Michael Polanyi informs that tacit knowledge plays a critical role in social communication, which is directly relative to the collaborative design process and communication. The integration of tacit knowledge may be reflected in the role of the designer and how they graphically represent intended designs. When the designer is conveying that idea, it is left for the client to reinterpret and articulate the embodied design intention. Those intentions may be lost or otherwise altered during the translation. Various design simulations such as drawings, physical, and digital models have been primary media for architectural design communication. Roderick J. Lawrence synthesized a set of principles towards the applications of design tools and methods. From these principles came about design communications methods in the form of tacit criteria. Real-time feedback, where users, clients, and professionals are encouraged to engage in interpersonal communication to enhance the quality of design decision-making. Context-specific, where users, clients, and professionals alike are able to experience design in proper context, accounting for existing site conditions. Full-scale immersion, where users, clients, and professionals are able to experience the design's proper scale, allowing interaction with the space prior to project implementation. An overview of the following standard practices of design communication have been investigated with respect to the embodiment of tacit characteristics. While conventional 2D drawings, typically seen on paper or on screen, conceptually delivers a sense of building form and scale, model integration serves to simplify design interpretation. With models, however, unless built in full scale and in context, the scale interpretation in models become difficult for many laypersons. The integration of virtual reality serves as an alternative medium complementing digital model making as it allows users to virtually walk through the design environment. Yet, although virtual reality simulations provide a full-scale experience, it lacks real-time context data. With the recent developments made in the field of augmented reality, or AR, specifically highlighting with the use of smart devices, the goal is to showcase its potential for AR to become an alternative media in capturing tacit knowledge during the collaborative design process and communication. AR is defined as the digital information that is displayed and overlapped onto the physical environment, creating an enhanced reality for users to perceive. Augmented reality allows designers to convey their ideas three-dimensionally through an environment that works to combine both digital and physical realities. The purpose for the use of augmented reality in architecture practice is to promote the embodiment of the user's tacit experience, such as real-time feedback, context-specific, and full-scale immersion during the duration of the project. This investigation, however, does not intend to replace conventional design communication media, but instead it introduces SDAR applications as an additional layer where deemed appropriate and expand the current toolsets that are readily available. Augmented reality, however, is not a new concept. The first appearance was seen in 1950. Over the years, technology has evolved from bulky machines to sophisticated pieces of technology. The benefits of applying augmented reality systems into architecture practice is that AR devices have the ability to be mobile in an outdoor environment, bringing the working designs out in a full scale and its proper context. It may also allow and assist with assembly as digital parts are used to indicate where pieces of the puzzle go. Additionally, designs are reflected across multiple devices that the design teams and clients can view same design from multiple viewpoints on the site. The multi-device application may also be reflected in the studio setting where design iterations may be made to view instantaneously. Industry experts identified 9 key areas of potential applications. Ranked in order, the highest application is to improve communication between architect, contractor, and subcontractor. However, this should not only encompass the professionals, but should as well include the clients into the communicative circle. The research outline for this project consisted of a series of applications to aid in the development of 3 scenarios. 1. Architecture element visualization. 2. Holographic assembly. And 3. Fenestration design with daylighting metrics through smart device augmented reality. The basis for each scenario consisted of Rhino 3D to be used for the creation of geometries, Grasshopper 3D to parameterize these geometries, and Hologram to augment objects from 3D model space into the physical environment, as well as synchronizing parameters onto the device's interface. The following scenarios showcase how tacit knowledge of real-time feedback, context-specific, and full-scale immersion are derived to support user implementation. Scenario 1 proposes an architectural element visualization for the School of Architecture's auditorium. The use of the smart device augmented reality will assist in the design development process by augmenting where the proposed set of designs will be located. The proposed application consists of 1. The initiation of SDAR, 2. The creation of architecture element, and 3. The visualization of architecture element. Given the design options created by the designer, they may allow the user to view the design both in context and in full scale. Through the screen of a smart device, while toggling between design options via parameters and layers, a recipe is made for conversation. Placement setup of the document's origin in order to project the proposed design onto the curve wall of the auditorium. Not only can the users and clients view the design, but they can also experience it while walking through full-scale immersion. They can also view it against the surrounding context, as well as interchanging the design option. They can also control the parameters, increasing or decreasing the density of the trellis. The application's versatility to be utilized in the design studio setting allows for quick iterations to be made on CAD programs and will automatically be reflected onto augmented models. The headset also provides a function to live sync to the Microsoft HoloLens app on a PC or desktop. This may be used to project to a larger conference screen. This is most beneficial when in a design studio setting or work setting or any setting that involves a large body of people for presentations. Scenario 1 architecture element visualization proved to be valuable as clients are able to articulate design skill much easier in relation to its surroundings. A holographic assembly revisits the tacit criteria as it enables users to augment a holographic set of instructions to assist a modular assembly process. The framework for the application of smart device augmented reality consists of 1. Initiating the smart device augmented reality application, 2. The development of the proposed structure, 3. The overlay of the digital objects, and 4. The assembly of the structure in the physical environment. This method proposes to cut down on time, errors, and subsequently costs for the duration of the project. The use of the HoloLens will be critical during this scenario as it frees up both hands for the user during assembly. It is not to say that smart devices are incapable of doing the job, but are instead more efficient for a headset to be used during assembly. In fact, the smart device may excel and serve for its user interface, while at the same time viewing the digital model and the physical space. Handling the blocks through HoloLens, smart device users will be in control of indicating the next piece to lay by toggling the slider. Working in unison, both the HoloLens and the smart device work to strengthen each other as these devices perform less as individuals and instead more as a whole. While directly applying the use of smart device augmented reality in the design process for interior daylighting, the user will be actively engaged in the design process. This allows for communication between users and designers about design intentions with real-time feedback simulations. The proposed application for Scenario 3 consists of 1. The initiation of SDAR, 2. The analysis of daylighting metrics, 3. The synthesis of the fenestration, and 4. The simulation of the synthesis outcomes. Aside from engaging the user into visualizing the outcomes, the focus here is to engage the user directly into the design itself. The user will be in full control of the actions taken while they are being overseen by the mentor, aka the designer. This is achieved by allowing the user with professional guidance to 1. The addition and deletion of the openings, 2. The translation of their location, and 3. The modification of their sizes. After the synthesis, the user reinitiates the simulation to see how their new opening configuration would affect the daylighting analysis results in conjunction with the real-time environment. Like Scenario 1 and 2, the location setup requires a QR code to place the model. Before making any changes, the first analysis is on the current design of the openings. After running the first analysis, the user may start to make modifications to the wall, adding, subtracting, changing sizes, and once again, they can run the analysis according to new changes. To reiterate, successful projects is the result of the architect-client relationship, where the relationship is born through a client's understanding of architectural understanding, because they undergo a state of habitus shock. And in order to realign projects' visions and goals, it is recommended for designers to integrate design tools that will cultivate the architectural tacit understanding. Augmented reality can serve as a catalyst to support tacit criteria in design communication. Achievements were made across all 3 scenarios. In architectural element visualization, what was achieved was that the user was able to walk under the trellis, viewing the full scale and in context. The user was able to toggle design options, viewing multiple designs. The user also was able to adjust the parameters for design type specific iterations. Multi-device connections were reflected across all connected platforms in a studio setting, and also as a live sync to presentation screen for the audience to view. In a holographic assembly, what was achieved was that the teamwork between HoloLens and smart device was in unison. The smart device user was controlling the block indicators that allowed the HoloLens user to be hands-free. And lastly, in fenestration design and daylighting metrics, what was achieved was that the design directly was driven by the client, who was also mentored by the designer. Modifications were made through clicking and dragging, adding or removing the windows by swiping on top the user interface. Parametric modifications for window sizes were made through the parameters of the interface, toggling layers to hide coded surfaces to show the openings. The user was also able to initiate the analysis of daylighting metrics, whether illumination, radiation, or exposure. They were able to do a full interior walkthrough, visualizing the design changes that they made, and also comparing metrics against reality for a better understanding for a different analysis date. All of these facilitating real-time feedback.